I want to chat a little bit about scaling some of the data structures that are inside the Tickle source code. If you all have read my, I was kind of surprised to see how much longer my abstract was than some of the other ones. So apparently I didn't get the sense of what the right length of those things was. And if I'd taken my cues, I wouldn't have written about more than I could actually prepare. So I'm sorry if you're using that as your guide. I'm going to get it graded incomplete today. But hopefully I'll say enough interesting things that you'll be satisfied. Thought I'd start out asking, who's seen this? Anyone run into this? So I asked Tickle to give me a list of 600 million A's, and it says, no, sorry Dave, I'm afraid I can't do that. I don't make lists that big. And that one actually comes back pretty quick, because you're asking it how long you want your list to be right off the bat, and Tickle just knows. Don't do that. Variation on it here is you can build the equivalent string. And Tickle will make strings that big, but then you ask it to treat it as a list and take the first element, and it needs to convert to a list, and it, again, comes back saying, sorry folks, that's too big for Tickle. Because Tickle has limits. More and more of them are actually called out in panic messages now than there used to be. There was a time when the way you discovered the limits was by having a crash that you didn't really comprehend. Most of these limits come out of the foundational fact that Tickle's memory allocation system can only allocate 4 gigabytes of memory at a time. So if you are storing things in big blocks of memory, once you get to a point where you need more than 4 gigabytes, we can't do it. So that's where most of these limitations have their root. You can make a case, and I actually, having been at the conference for a couple of days now, I regret this bullet point I'm on here. Many arguably not a bad idea, but this is a common retort, I think, in the Tickle community, where you come across something that Tickle can't do or can't do particularly well, and the comment comes back and goes, oh, you shouldn't be trying to do that in Tickle. That's not what Tickle's for. What are you making 500 million linked lists for in Tickle? That's not what Tickle's for. You should be using something better suited to that task. And, you know, that position has some merit to it, but coming here to the conference and hearing about all the really big tasks that people are actually putting Tickle to, at least in this audience, that's not the right answer, and I don't think it's the right answer. Even if Tickle gets to the point where it can't handle something terribly well, I think it's better to just start handling it badly than to throw in the towel and give up, which is what it does on some of these matters. Tickle quits before your memory does, and Tickle 9 really shouldn't. So I thought I'd chat a little bit about one of the foundational features, foundational stanzas you find throughout the Tickle code called the so-called Tickle string growth algorithm. At least that's the term. I always knew it by the name. I came to learn about it. And it's pretty simple in its simplest form. I've got an array, and I need to put something in that array. If there's already enough space in the array, I just do it. But if I'm at a point where, I'm sorry, that next bit that you want to put in, you don't have enough space for that. Say, okay, well, give me twice as much space. And I got that in quotes here, double the size, because there are different refinements on what you're actually doubling. Some of the places will say actually double the size of the array. Some say double the size you are going to be needing after you append the part you're appending. There's a few variants on this, but that's the general twist of the algorithm is use it as long as you can, you run out of space, double the size, forge on. And there's various refinements to this. One of the biggest ones is a lot of these dynamic arrays start out with an initial static buffer. So you start out with some size, and usually these static buffers are sized so that they cover most of the cases. So in your normal Tickle use, you aren't doing any of this dynamic allocation at all. You're just using the static that you've been provided. But then when you need to grow big in those strange cases, the double the size algorithm takes over. Another place where there has been some variance on this, you can imagine as you actually start to push toward the memory limits of your machine, if you are at the point where you are using a gigabyte and you need to use a little more, the fact that the system won't give you 2 gigabytes is perhaps not a cause for crashing the program. Maybe you really should be allowed to ask for 1.1 gigabytes. And so some of the places where this algorithm is in place have put that additional wrinkle in. Let's fall back. If we keep failing, well, try a little less until you really hit the point where you really can't get what you need, and then it will fail. There's also some tricks in there about minimum growth rates, so you don't always append 1 more byte, and 1 more byte, and 1 more byte. And it's not just for strings anymore. I call this the string growth algorithm, and it probably shows up most frequently frequently is the wrong way to put it. I think of it as having its roots in the Tickle D string struct. It may or may not actually have its roots there, but that's where the name seems to fit. But the same algorithm is in the core again and again and again to grow just about anything that you need a large collection, or you need a potentially unlimited size collection of. And so some of the things managed in that manner are Tickle tokens, which is the system by which the parser operates. Op nodes, which is how the expression parser operates. When you have a list value, the list value is actually stored as a dynamic array of Tickle value pointers, Tickle OBJ pointers. That can grow in the same way. In the bytecode compiler and execution engine, you've got the bytecodes themselves, the exception ranges, literals. It just goes on and on and on. I thought I would note here that there are a handful of things in the core which need this potential for unlimited growth that don't take this approach. And probably the big one is hash tables, which actually does a multiply by 4 and rebuild the table strategy when it decides it's no longer functioning well on the current size of bucket lists. And the other thing is the fairly new OO things haven't really taken this approach. They've done much more of an incremental, we will grow the array as we need, but we're not going to do this doubling strategy. We're just going to grow by some fixed chunk, which seems reasonable. And I really don't know the pros and cons of that, but that's something that's in the core, and it's a bit different. And what's good about this string growth algorithm? Well, it does what it needs to do. It delivers dynamic arrays. You can make use of these things and just transparently see things get bigger as they need to get bigger so that you can have unlimited size of various things you need to potentially have unlimited size of. And it's only the memory bytes that, the memory or this limit bytes that you run into trouble. You can look up from these things in constant time, and you can append to them in so-called amortized constant time. Every now and then you're going to double the array. That's going to cost you something. But most of the time you just stuff in the memory you've already got, and the growth occurs at a frequency which is matched by the frequency of the append. So you average out all the appends and it's constant time. Another thing that's really good about this particular strategy is that at any moment you can ask for a pointer to the beginning of your dynamic array and get a pointer to an array that as a C programmer you can just use as an array. All the familiar programming tricks and techniques and patterns you're aware of, you just use them. So I want to manipulate my string as a char pointer, constant char pointer. Tickle D string value gives me the pointer I need, and I can just use it. If I want to pull the set of values, the elements of my list, Tickle list object get elements, it's now in my object V array. But what's not quite so good? It's got some downsides. And the one I put first is the one that caught my attention first. And it's the fact that this algorithm is coded again, again, and again, and again, and a few more times again in the core. It's such a great idea, but we've never actually had the idea of wrapping it up as a utility proc that we could perfect one time and keep reusing. Instead, every time this kind of level of dynamic array is needed, Whoever's putting it in puts in a static buffer and a doubling algorithm and a routine to compute it over and over and over again. So I see that, and that bothers me, so that's why I put it at the top. It may not be actually the most important thing, but I like to call attention to it. One of the other problems, potentially, is that at that moment where you decide, hey, I need more memory, and I double it, I've got as much memory allocated but not being used as I have being used. So the amount of memory I'm wasting is equal to the amount of memory I'm using. And even on average, you've got an amount of wastage of memory which is of the same scale as the length of the array you're storing. One of the other features of at least most of the implementations of this is that once the memory is allocated, it doesn't go away. It doesn't shrink as your need for it goes away. So you have this high watermark effect that your storage is as big as you ever needed until you get to the point where you throw the whole thing out. Throw the whole thing out, then you collect it all back. Or at least you return it to some pools where it can be reused. And for a lot of the uses in the core, that's fine. Tickle token is a good example. You're going to parse some big text script, and as you go, you're going to create another token, and another token, and another token to build your description of what that text script is in the sense of the structure of a Tickle script. You're not going to shrink that. So if you're going to code a dynamic array for just that task, yeah, you shouldn't bother putting in the shrink logic because you're never going to use it. But this gets back to the coding it again and again and again. If you were to code it one time for reuse, you'd want the shrinkage put in for those applications where you are going to grow and shrink and grow and shrink your needs as things go on. Finally, this last point, depending on what you're doing, the fact that the returned pointers are not stable can be an issue. What do I mean by that? So I've got my dynamic array, it's storing a bunch of whatevers for me. And at some point, my code needs to find the 10th whatever. So give me a pointer to the 10th whatever you're storing for me. I give back a pointer to it. And I've got it, I'm holding it in the pointer variable. Now the question is, how long can I keep using that? The problem is, if I hold it over here long enough and the rest of the program goes on and does things, if the need comes along that needs to grow, there'll be a doubling of the allocation, which can move the entire thing from its location in memory to some new location in memory. And I'm left with a pointer pointing to what used to be the 10th thing in my collection. Now it's pointing to freed memory, or worse, new memory used for a different purpose. So this is something you always have to be aware of when you're pulling back pointers from these things, and you have to deal with it. Some things it doesn't matter, some things you don't do that kind of thing, but some things you do. So, is there any other option? Oh yeah. And here's where I confess the magnitude of my ignorance. There are lots and lots and lots of ways to do dynamic arrays out there in the computer science world, more than I know anything about. And this is where I try to make absolutely clear I'm not standing up here as some expert computer scientist who has surveyed the entire domain and carefully pulled back the perfect solution to the perfect problem. This is enough said. But it is one I can tell you about. And that's something I call the Broadneck Array. I don't know that anybody else calls it the Broadneck Array, but I call it that because I learned about it by reading a paper where a fellow named Broadneck was the first author. So there's the citation for anyone who likes to follow up and check the references. This is a different way of structuring dynamic arrays, which I think has some benefits, has some drawbacks. But it's something I think it's good for us to be aware of and to potentially use where it makes sense and not use where it doesn't make sense. So let's see if I can describe a Broadneck array. Rather than storing your sequence of elements in one continuous block of memory, a Broadneck array will store a sequence of items as an index array where each element of that array is a data block array. So you're trading a one-dimensional thing for a two-dimensional thing. Okay? So if you imagine that initial array, we'll call it store. It's sitting here holding the pointers to the data blocks, which are the store sub high. I'm going to use index pairs called high and low to represent the two dimensions of the structure I'm getting into. Now, as the index in that master store array increases, the length of the data blocks that are stored there grows. So that the first few have only a handful of elements, but as you get further down the array, you get longer and longer and longer data blocks. In particular, the first data block's got only one element in it. But if you look at the, let's say, 2 to the n minus 2 data block, it actually holds 2 to the n items, and it begins at index 2 to the 2n minus 1. I don't know how good you are at manipulating figures like that on the spot, but the key thing I wanted to point out about it is if you're at index 2 to the 2n and you're starting to fill a data block of 2 to the n, each data block is roughly the square root of the size of the array. So as you're growing and adding that next data block to sustain the growth of your collection, you're adding square root of the size of your total collection rather than n, rather than something proportional to the length of the collection. Yes, sir?
So I'm confused. Aren't you effectively doubling the total number of items allocated each time you extend that block?
I don't think so. This is where I wish I had taken the time to draw a diagram rather than put algebra in place. But
if you think about, you've got 2 to the n items you've currently allocated in the last block. The next one is going to have 2 to the n plus 1 items, which is roughly equal to the sum of all previous items, right?
No, and I've been unclear, unfortunately, in my presentation. The size of the data block does not grow with each step. So let me talk you through the first several data block sizes, and maybe the pattern will become clear. And if it doesn't become clear now, it should become clear in the next slide where I talk through how you do the transition between indices. The first data block has a size of 1. Second data block has a size of 2. Third data block has a size of 2. Fourth data block has a size of 2. Fifth data block has a size of 4. And then it goes 4 up through 6 of them. Then it goes 8 up through 12 of them, and so on. So the spacing between the increase in size also increases as you go. So what you end up with is not a doubling at each step, but a doubling at each so many steps so that the growth of the entire thing is a square root n growth. Hopefully that at least, if that doesn't help, hopefully the next slide will. So here's where I actually wrote a little Tickle script to illustrate the mapping between the index into the one-dimensional collection and the two-dimensional indices that will actually get you where you need to be in this storage collection. So we start with the index at 0, our high index at 0, our low index at 0. Apparently I abbreviated count once and then didn't elsewhere, so please make that correction as you read. And then size of 1. So size here is going to be how big that next data block is going to be. So if I just put a while one loop, so I'm going to go through, and I say I didn't anchor my I either, so you'll have to implicitly put that one in as well. Apologies for that. But we'll start out with index 0 is stored at location 0, 0, the first element of the first data block. If I increment that low index and I stay within the size of that data block, I'm done. I can just count down the data block until I run out of it. So then I just continue. And that's where this should be a for loop instead of a while loop. That would have taken care of it for me. However, if I've reached the end of my data block, I reset the low index to 0 to start the next data block. I anchor my high, get me to the next data block. And this count that I've been keeping, if my count is 0, then it's time to increase the data block size. And the key here is that that count itself is not static. It grows as the structure grows. So I set the count to my current size. I double the size so that my next data block is going to be twice as big. And then I increment the count by the size as well. So that effectively it becomes you have 3 times the size of the data block as you go forward. Now that's an implicit way of seeing the relationship between the two. Fortunately, there's an explicit way to do it, because if there were only an implicit way, computing the index map would be prohibitive. It throws us right out. So here's a different way to see how to take an index in the single dimension collection and convert it to a pair of indices in the 2-dimensional collection. So I'll start as an example. I'll start with the number 77 and write it out in binary form. So trust me, that's the binary form, or do a format %B. It's got a leading bit, and then you take the remaining bits and cut them in half. So I've got a collection of bits here to help map to the high, and a collection of bits here to map to the low. First part's easy. These bits, they are the low. That's the low index. And because the reach of that index by the size, by the number of bits in it, is 3 bits, I know that I'm counting through a data block of size 8, 2 to the 3. The hand-waving bit is that you have to trust me a little bit. I can take these bits here, combine it with that 3, and can compute directly that the value of the high index is 15. So if I apply the algorithm, I can take 77 and map it to the pair 15, 5. Now the additional wrinkle here is that this algorithm relies on there being a leading 1 in your binary expansion. The number 0 doesn't have a leading 1. So before you apply this transformation, you actually shift your indices by 1. So all this stuff that I told you about the number 77, I was fibbing. It's really the number 76 that maps to 15.5. The key thing is that this calculation can be done, and it can be done in constant time. There's no order n need here. One of the interesting wrinkles about it is a key step is computing what bit position is the most significant of your index. And this is something processors can do, but C doesn't give you easy access to. So it's one of those cases where it's actually worth your time to find out what your compiler specialty directives are for reaching into processor capabilities that otherwise aren't in the language. Now, growing and shrinking. So as you're appending, at some point you reach the point where it says, okay, well, you need to go to the next data block. The next data block's not there, you just have to allocate it. And since that allocation is on the order of square root of the size, you've got a growth of square root of n as you go. As you're going back the other way and shrinking, the rule is you keep at most one of those data blocks around that you're not actually using. So at any point as you grow and shrink some more, you're never at a point where you've allocated more than square root of the size that you're making use of. Now that's talking about the data blocks. You also have this master index, which holds the pointers to your data block. You just use the string growth algorithm on that. That's good enough. Double it when you need to double it. And the other thing you add is that if you ever get to the point where you only need a quarter of what you've been using, go ahead and reallocate it and lop it off. Now you're reallocating there, which means that that store array can move to different parts of memory. But the data blocks don't go anywhere. So summarizing some of the good features of the Broadneck Array, you're only wasting order square root of n of memory instead of order n. It's coded from the beginning to release the memory it's not making use of. It has the same complexity features as the dynamic array with the string growth algorithm. It can look up in constant time. It can append in amortized constant time. Granted, the constants are a bit bigger. That may matter. It may not. Here's one of the nice things. The data doesn't move. That index array comes and goes, shifts around. The data blocks, so long as you haven't actually shrunk away and thrown them out, so long as they're still sitting there, they're still holding your data, they're still holding it at the same place in memory. So if you grab a pointer pointing to one of those things, and you know that it hasn't been thrown away, you know you're still pointing to it. And this is, my prejudice again showing up here. This is a complicated enough data structure that you'll only code it one time, and you'll reuse it. I mean, the reason people don't do that with the dynamic arrays is just fall off a log easy, so why don't you just write it again? What's maybe not so good about the Broadneck Array? Well, it's unfamiliar, and it's hard to describe in a short period of time. It also lacks the ability to just grab a pointer and go. One of the nice things about the D string, I ask for the D string value, I get a const char pointer, and I know what to do with that. I can get a pointer to an element in a Broadneck array, but how many more elements after that one can I just increment the pointer and go get? It's not something that's easily computed. You have to basically leave it up to the data structure to tell you. If you want to copy a range, you have to say, Broadneck array, copy me a range. And here's where you can copy it to. Or learn some interfaces. Another potential problem, since it's a two-dimensional structure, if you're randomly looking up an element in the array, you're doing two memory accesses. Whereas with a plain old C array, you only need to do one. That may matter. And it may not. And I say it's a complex question because in the back of my head I'm thinking, well, sure, the actual act of randomly retrieving one element from my array is going to be slower. I don't think you can get around that. But if the capabilities of the data structure let you change your code in other ways, it can be balanced out. Pulling things from memory is so far removed from your CS 101 notion of what it means to pull something from memory. I don't know a simple way to analyze this, other than just to implement it and try it out and see what happens. There's so much multi-level structure, there's so much caching involved, and so much of memory performance depends on whether or not you hit a cache, miss a cache, whether it fits in the high-speed memory you have, or whether it has to shift out to the low-speed memory. Remains to be seen. I think you have to test that in reality. The other thing which tends to mitigate this particular problem is that actually random access lookup is not all that common in programming. It's much more frequent that you want to scan through an array. You don't necessarily want to jump here and there and everywhere. You want to start at the first one and go to the last one. And you can actually do that without paying this penalty of two memory accesses. And I'll show you how in a minute. Another problem that, at least with a naive implementation of a Broadneck array, I was describing the size of the data blocks. First data block, one element. Second data block, only two elements. I mean, how often when you're going to bother to create an array, do you only need a handful of elements? So the price of the shrinking and growing and shrinking and growing and allocating a block for each of these tiny things just to get up to a collection of, say, 50 is not really sensible. So you should do the same kind of strategy that the dynamic arrays on the string growth algorithm do. You ought to have a static buffer to start you out. It's simply a matter of programming to put that in, but it's not put in.
Well, Dennis, start with a constant other than 1 for the data block size.
That's another way to go. The difficulty with that is the impedance mismatch it introduces in the sense of how people want to index into arrays. You can shim it. You can just, in between, every time you use the array, put in the plus offset. But in other words, if my Broadneck array is going to start indexed at 100, that would work. But then everybody who uses it either has to know that and start all their indexes at 100, or they have to use it the way they're used to using it, zero-based, and something in between adds
Or
100.
they call the interface to say, here's my index, give me the pointer, and maybe the 0th element of the index is the size.
The real question is whether indices only come from the data structure itself, in which case it's perfectly fine, or if they have some other connection to other things, where for some reason you want it to be zero-based. But yeah, you've hit on quite a feasible answer to the question. So here's a way around the double memory access if you're going to do sequential access. It's called the Broadband Pointer. If you've worked with various types of standard template libraries or anything like this, you're probably familiar with the notion of an iterator. And so this is basically just the idea of an iterator going through one of these Broadneck arrays. You call it a Broadneck pointer, and it remembers where it got the thing you assigned it to. So when you want to go to the next one, well, almost all the time, the next one is the next one in the data block. All you have to do is advance the pointer. It's only on those occasions where you have to go to the next data block where it's anything different from that. And so long as that Broadneck pointer can keep track of what block you're on, what size it is, how much more you have to go, you can step through these things with single memory accesses and not a lot of additional overhead. So here's just that, that example in code. So if you've got the traditional array where you're scanning through with a for loop, you're accustomed to just taking the head of the array, assigning it to a pointer, and just increment the pointer and make use of the pointer in your loop. I'm actually fudging a little detail here because I'm saying, I'm just going to test until p is at the end. And these Tickle string growth algorithms, you have to know where the end is. So that's actually a little detail I'm fudging there. Contrast that with, if I'm going to do the Broadneck array, I create these routines to take care of a lot of this stuff for me. So I say, give me a pointer into the structure that's first, and also in this Broadneck pointer, keep track of where I am. And then the increment is, okay, go to the next thing. And as I go to the next thing, on the way out, give me a pointer to the data at that point. And the novelty here is that the way you determine you're at the end is get returned to null value. Pointing in instead of giving a pointer to the next element, there is no next element, you get a null. And that's how you know to quit. So it's got some nice features, but where is it missing the target? These are really good for stack-like things. You can grow them and shrink them and grow them and shrink them on the end. But if you have a need where you're routinely going to need to yank a sequence of things out of the middle and collapse it all down to fill the hole, Broadneck arrays don't do well with that. Likewise, if you need to stick some chunk in, don't do terribly well. You can't avoid any real copying tasks because you've got